right, so our third paper, our third paper is from, will be presented by Hossam, and he's from University of Waterloo, and I believe he's looking for internship. Okay, and the paper is BliMe, verifiably secure outsourced computation with hardware-enforced taint-tracking.
Thank you very much. Hello, everyone. My name is Hossam. I'm a PhD student at the University of Waterloo, and I'm going to present to you our work today on blinded memory, or BliMe for short. All right. Okay, so the scenario we're targeting here is outsourced computation, right? So the goal is to run some server's confidential code on a client's confidential data. So a prominent example here is something like outsourced machine learning inference. So in a traditional example, you'd have a client send their data to a server. The server must see this data to be able to process it, get a result, and then send the result back to the client. And as you can see, of course, this presents confidentiality risks to the client. And there are existing solutions to this, such as fully-homomorphic encryption and multi-party computation. Now, these cryptographic solutions have very large overheads, usually in the order, multiple orders of magnitude higher than native execution. The other alternative is to use hardware-based isolation and remote attestation. This provides very low overheads and usually comes in the form of trusted execution environments, something like Intel SGX. Okay, so trusted execution environments provide an isolated environment for the execution of software, but they do come with their own caveats, right? So they are generally unsuitable when the server code is confidential, proprietary, or unverifiable, right? And TEEs in general are intended for the use case where the client must be able to verify or trust the code that is running on their data. In addition to that, the confidentiality of TEEs is hampered by two things. So the first is that they have a large code base, which makes them vulnerable to software vulnerabilities and runtime attacks. And the second is that they share resources with the rest of the software on the system. So that makes them vulnerable to side channel attacks. And the majority of commercial TEEs do not have side channels in scope in terms of their attack surface. So just to set the landscape here, this is a graph of performance versus confidentiality, and on the top right corner you have vanilla outsourced computation, which provides high performance, but it also provides low or no confidentiality. Current TEEs provide some confidentiality guarantees and also provide low performance overheads. On the other hand, you have fully homomorphic encryption, which provides very high confidentiality, but as we said, suffers from very low performance. And our goal with BliMe is to introduce something in this area, which has high performance and also has confidentiality guarantees comparable to fully homomorphic encryption. And the key to do this is to use hardware assistance. Okay, so what can we do, right? So the first thing is we can prevent application software from leaking sensitive data, and we do this using hardware-assisted taint tracking. This allows a client to give the server their data without trusting the application software. The second thing is that we can minimize resource sharing, and we can do this by moving critical operations such as key management and remote attestation to a fixed function isolated module, an HSM, hardware security module. And the code of this HSM can be analyzed in advance and guaranteed not to be malicious. Okay, so for the first thing, how can we prevent the leakage of sensitive data? And we do this using CPU extensions, right? And the main idea here is that safe streams of instructions do not expose sensitive data. So that means we can allow computation on the sensitive data by arbitrary, unattested, and untrusted software. But we have to make sure that any operation that can leak sensitive data into observable state is prohibited. Examples of observable state here are things like peripherals which are outside the security boundary, like a network interface card, for example, or things like micro-architectural state, such as cache state, right? And to do this, we use a taint-tracking-based security policy, which tracks the sensitive data and limits it only to safe places within the system. For the second part, for the HSM, we combine the CPU extensions with an attestable HSM to assure the clients that the security policy is in place on the server and their data is subject to that security policy. And this transforms the server into the following. So now you have the server with a trusted part, which consists of CPU extensions and the fixed function HSM, and the untrusted part, which is the application software. And now what happens is that the client can send their data first to the trusted part of the server. It becomes tainted, which we call blinded. And then this blinded data can be sent to the application software. The application software is now free to operate on this blinded data, subject to the security policy enforced by the hardware. Once a result is computed, it can then send the result back to the trusted part of the server, which can then unblind the result and then send it back to the client. Okay, so let's get into a little bit more detail. How does this taint-tracking policy actually work? And the idea here is that registers in memory have an associated sensitivity bit attached to it, and we call this a blindedness bit. And we have a taint propagation rule, which says that if any input is blinded and the output depends on this input, then the output also becomes blinded, right? And the goal we're trying to achieve is that any changes in sensitive state can never affect the visible non-sensitive state, right? So we'll take a concrete example. So let's say you have registers A and B here. B has blinded data in it. And you have an instruction that takes these two as input and then outputs the result into register A. And as you can see here, register A has now become blinded because it depended on register B, which was also blinded. If we take another instruction, so something, let's say, that writes an immediate value into register A, so it doesn't have any blinded inputs, now register A has become overwritten and it's no longer blinded. So we just discussed taint propagation in terms of registers and memory values, but there are other things that we need to consider in terms of observable outputs. One prominent example is control flow. So if we go back to our example, if we have an instruction here, such as a jump, that uses a sensitive value as an address, so something in register B, and what that would do is it would then taint the program counter, and this would make it observable to an adversary. In this situation, we actually force a fault, so we prevent the application software from performing this operation, and this prevents the leakage of sensitive data. There are other observable outputs that we also need to consider. So exceptions fall under the same category as control flow. We also have memory access patterns. So for example, if you have a load or a store that tries to use a blinded input as an address, that would also cause a fault. And the idea here is that some of these outputs cannot be marked as blinded. You cannot attach a blindedness bit to a memory access pattern. So what we do in this case, if there's any data flow from a blinded value to an unmarkable output, we yield a fault. Okay, so if we put all of this together, we get the BliMe architecture, right? And now, as you can see, the server has the following, right? It has the hardware with our CPU extensions. This also includes an encryption engine, which exposes two operations, a data import operation and a data export operation. And it also includes the fixed function HSM, which has the key exchange engine, which is in charge of key management with the client and remote attestation. So the first thing that happens is that the client communicates with the HSM to initiate a handshake. It performs remote attestation to ensure that this is genuine BliMe hardware, and then agrees with the HSM on a set of keys. And these keys are then stored inside the encryption engine, right? So what the client now does is it encrypts its data with these keys, sends them to the server, and tells the application software to please invoke the data import function. What this data import function does is it atomically decrypts and blinds the data. So now you have blinded plain text, which you can give back to the application software, and the application software can now do its computation on it. It can do arbitrary computations. We don't have to do any form of code attestation. And the security or the confidentiality of the data is enforced by the BliMe hardware extensions. Once the result is computed, the application software can then invoke the data export function. What this does is it atomically encrypts and unblinds the data, and then this data can then be sent to the client, who can then decrypt it and get the result back. All right, so in terms of implementation, we implemented this in RTL on the speculative out-of-order RISC-V boom core, and we did this using tagged memory, so each word can be marked as blinded. We also added instructions to mark physical memory as blinded or unblinded, and it also does the encryption and decryption. We also implemented taint tracking for all the instructions in the RISC-V set. And what we did here is that we, if there's any input that is blinded, the output is automatically blinded. You might have noticed that this is an approximation of the earlier rule that we talked about. It is slightly more conservative, but it's also easier to implement. Okay, so we talked about side channels and microarchitectural state. So it's also important to mention speculation, right? And the key idea here is that the same security policy must be enforced during speculation, right? So that's what we do here. And this means that any instructions that will cause side channel leakage, even speculatively, will fault. And if they are speculative, this fault will be suppressed until they no longer become speculative. Right? Another thing is that blindness must be tracked throughout the processor microarchitecture. So within the processor, data must carry its blindness bit with it. That means that this is carried with it in things like line fill buffers, load store queues, and other buffers within the processor. And this is actually ensured by the Chisel RTL type system. So Chisel is the language in which BliMe is written. And we just create a new Chisel type, and the compiler helps us find any mismatches in the RTL. Okay, so far we've only talked about just perspective of a single client, right? And if we have a single bit, it can be very easy for a server to just swap data between different clients, right? And what we actually need is a separate sensitivity domain for each client, and then just swap keys in and out on context switches. And the way we do this is to actually introduce hardware support, right? So instead of a single bit, we now have multiple bits, a multi-bit blindness tag, and this allows the system to be secure even if we have a malicious OS, right? We have another weaker threat model that is also in the paper. Please read that for more detail as well. For evaluation, in terms of compatibility, what we wanted to check here is that if we have code that is already side channel resistant, would it be able to run on BliMe without modification? And we managed to do this with the tweet-knackle crypto library. So this is, we're able to run this without modifications. And in terms of overhead, so we implemented this on an FPGA. So we have an area overhead of 9% and a power overhead of 1.4%. For performance, we ran the Spec 17 benchmark suite, and we got a geo-mean of 8%. We ran the Spec 17 benchmark on Gem 5. For technical reasons, please refer to the paper on why we did this on Gem 5. For security, we also have a formal verification in F-star. So we modeled BliMe in F-star, and we verified that any changes in blinded state never affect the non-blinded state. You can also find this model in the link below, and it's also available in our artifact evaluation package. Okay, so far we've discussed BliMe, but what about the software that runs on top, right? And we might have noticed that there's a slight problem here, which is that software might not run as is, right? The BliMe hardware extensions will abort any non-compliant code or any non-secure code, right? You can take software and hand port it. So we managed to do this with the TensorFlow Lite library, and we're able to run inference. But doing this by hand for all software is tedious, it's error-prone, and it's actually made more difficult by things like compiler optimizations that might introduce side channels. As you might imagine, this presents a usability challenge, right? So just to reiterate, this is not a security challenge because the security is still guaranteed by the hardware, but it is a usability challenge because you don't want your software to fault or abort. There are existing solutions that try to perform the same thing, such as Constantine, but they're not applicable as is. They use things like dynamic profiling, they under-approximate taint, and they use a best effort approach. So our approach is mainly to focus on static analysis, and this is actually ongoing work. Okay, so to summarize, BliMe provides FHE-style security, but efficiently. It allows us to safely run untrusted code on sensitive data. We've implemented this for Boom, which is a speculative out-of-order RISC-V core. And we also have ongoing work to provide compiler support for usability to make transformation of code automatic. You can find everything in the QR code on the right, the paper source code. We also have the artifact evaluation package. We managed to get all 3 badges, so please check it out. Thank you.
All right, awesome work. Questions?
Hi, thank you for the great talk. I'm Hyung-gon Moon from UNIST. So I really love this work. I really want to use it. But my question is that, so why do we need this taint tracking? Why we cannot just prevent the remote software from just exposing any data to the host?
So, so the thing is here, we implement things like enforcing a constant time policy on code. So trying to do this for all code on the system is too much. It's overkill. It'll kill your performance, especially when you have operating system, for example. You don't want to enforce a very strict security policy on all data. And when you compare also the ratio of sensitive data within non-sensitive data in the system, you don't really care about the sensitive data. You don't really want to enforce it on all the data in the system. Does that answer your question?
Okay, then it seems the like argument using the constant time execution might be really convincing. Thanks.
Okay, nice.
Nader Salbash, UCLA. Thanks for great presentations. It's such a fundamental work. Really, I really enjoyed it. So did you get a chance to kind of compare this with other existing taint tracking, especially for speculative, like SCT? I don't know if you're familiar with that.
Yeah. Yeah. So we do discuss SCT slightly in the paper, but SCT sort of it targets a different thing, right? So it only targets transient execution attacks.
Yeah, just speculative.
Yeah. What we do is, even if this is in the non-speculative domain, even if you have some code that is insecure by design, we also prevent that, right? Because one thing that we also care about is malicious code. So let's say you have a malicious server that just wants to extract your data. You also want to enforce a security policy.
Yeah, I think because one downside would be like the performance overhead would be much higher, right? I think you mentioned 8% versus. Is there room in your design to kind of get it closer to something like SCT?
Yes, definitely. So actually, the 8% we got was there is room for improvement. So I mean, the sole reason for the overhead is from the tagging, the memory tagging. And this is, so what we implemented was without a tag cache. So if you use a tag cache, you can reduce this performance much more. And if you look at commercial memory tagging implementations like ARM MTE, they have, I think, like maybe 2 or 3% overhead. So it's much lower.
Thank you so much.
Hi. Sorry, maybe I missed something. So I didn't see how the hardware guarantees constant time.
Yeah, so we prevent any operation that can leak the data through side channels. So we identify things like, so I mentioned control flow. If there's a, for example, an if condition.
But that's not constant time, right? That's not constant time guarantee. That's a taint. You're using taint, right?
Yeah, but if you have tainted data that is used in any form that can leak because it's not constant time.
No, I mean you just leak through the timing channels.
Yeah, so that's exactly what we prevent. So if there's any operation that would leak the data through timing channels, like affecting cache state, or because, for example, the instruction takes a variable number of cycles, all these things are things that we prevent. So we can, because we modify the CPU, we know what each instruction does, and then we can just say, if these inputs are blinded, then you have to abort the.
But normally for modern CPUs to gain efficiency, instructions do take variable number of cycles.
Exactly. So in our case, for example, what we can do is if it detects blinded data, it can take the worst case, but only for the cases where there's blinded inputs and not for the general case.
Oh, I see. Okay. But then the overhead should be higher than 8%.
Oh. Actually, I think the main reason the overhead is not very high is because all of the taint tracking and even the enforcement is done in parallel. So it's not on the critical path. It doesn't add any additional cycles. The only cycles that we add is actually just for the.
No, but what about the cache?
For us, for the caches, each cache entry has the tags for the corresponding words inside it. So the only cycles we add are actually between the last level cache and the main memory. Right? So once you're inside the cache, every data has its own blindness tag, and you don't have to introduce any additional cycles.
All right, so I think we have some time, so I can ask a clarification question.
Sure.
So sitting between the last level cache and the memory, is there an encryption engine that encrypt data when it leaves the CPU to the memory?
Okay, so it's actually a good question. So that's not the encryption engine that I mentioned here. So the encryption engine is sort of like an additional module
Yes,
within
I
the
know.
CPU.
Yes.
But we can introduce like a sort of transparent layer encryption between the CPU and the main memory,
Okay.
and that would prevent things like cold boot attacks, for example.
Yeah.
So these are things that for us are out of scope, but there
Okay.
are already orthogonal
Okay, so
solutions.
right now, basically, if I tap the bus or if I probe the memory, I know the clear text.
Yeah,
Okay.
so yeah.
All right. All right. So let's thank the speaker again. And